AWS architecture gets into pulling together all the things that we've talked about. Cloud architecture really gives you the ability to leverage things like awareness of what are the best practices, thinking about foundational areas that are often neglected, and also looking at different kinds of architectures and using a consistent set of principles. So one of the things that AWS has come up with that is helpful is something called the well-architected framework. And really, it's a way of providing a set of best practices that you can use when you're actually going through and architecting a system on AWS. So some of the things that it does not provide is it doesn't get into specifics about, how to do something. So the implementation details or some specific pattern like serverless or something like that. And another thing it doesn't do, so we'll say this is no, is it also doesn't go in and give you, let's say, case studies. Instead, what it is it's a way of asking critical questions and also providing relevant answers about services and solutions. So let's talk about some of these pillars here of a well-architected framework. To start with, you've got operational excellence. So this is your ability to deliver value, right? So what is your ROI? Is your system actually doing what you hope it's doing? Another one is security. So we just talked about security recently, but can you protect your system, or do you have S3 buckets that are exposed that are leaking customer data? Reliability. So can you recover from failure? So do you have a system that's going to be able to mitigate a disruption? And then what about performance efficiency? Are you using things, maybe the right type of instance versus an instance that's too large? And then also cost optimization. So are you getting rid of resources that are maybe unneeded? For example, have you spun up maybe a development cluster that doesn't need to be the size it is, or maybe it could be shut off at night? So there's lots of different ways to think about this cost optimization. Now let's break these down one by one. So in terms of operational excellence, a few different ways to think about this would be the business value, right? So in terms of your business, is your architecture actually doing that? So a few different key topics would be how to manage and automate changes, how to respond to events, and how to respond to changes. Now let's get into the next section here, which is security. In terms of security, are you actually able to protect your system? That's really the number one thing to consider. So this means things like the assets. So let's say your image files or video files, your customer transactions, and also are you still delivering business value through using things like risk assessment or mitigation strategies? What about reliability? Reliability is an important one to consider as well. And what this means is recover from failure. So things are going to fail. That's a given. And so what is the architectural configuration that you've got set up to account for the fact that failure will occur? So you can say, failure is guaranteed, but what isn't guaranteed is what are you going to do about it, right? So what is the action your architecture is going to take to account for that failure? Let's go into performance efficiency here as well. So performance efficiency is really using something effectively, right? So are you actually going to spin up the correct types of machines, maybe a CPU in one case or a GPU in another case, or a memory optimized instance? And a lot of this is about using the resources sparingly, right? So you're meeting your requirements, but you're not overdoing it with the resource that you've picked up. Another one to be aware of is cost optimization. And so with cost optimization, one of the things that you look at from an architecture is, are there things that you can get rid of, right? Are there unneeded costs? And this is a constant battle. And most of the startups I've worked at, this is something that's really important that many companies don't do. They'll have, let's say, a $20,000 a month bill, and really their resource usage could go down to $2,000, right? So they're using 10 times more resources than they have to because they haven't automated parts of their system. So a lot of this is by using cost-effective systems like looking at the trusted advisor, for example. So a few different design principles to be aware of are that you can adopt a consumption model, you can measure the overall efficiency, and you can reduce spending on operations. And also you can use more managed services. So when you use managed services, this actually allows you to take off some of the burden, right? So you can use these all the development work that AWS has given you. So let's talk about some design principles now. So one of the design principles to be aware of in terms of this well-architected framework is capacity. And so what capacity design principle is that, are you guessing about how much you actually need in terms of resources, or are you actually planning it, right? And so have you set up an ecosystem where you have, let's say, a load balancer with different nodes attached to it, and you can scale those up and you can scale those down by using things like CloudWatch health metrics, or are you doing something like you're doing in a traditional environment where you've actually got over-provisioned or under-provisioned resources? So this is a huge design consideration, is do you actually have the ability to have the correct capacity of your system? Another architectural thing that happens a lot, and most of my career, in fact, I've been involved in this, is are you actually testing your system at scale? So let's take a film system or a game system or social network system. Is you have to go through the scenarios where your system will be in used, and then you actually have to duplicate that environment. So do you have a duplicate environment? And oftentimes that's called the staging environment, where you actually can run through and look at a scenario. Like, let's say you've developed a game, and then that game you expect to have 100,000 users on it at a given time. So have you actually load tested all of those 100,000 users on that staging environment, which is a duplicate of your environment? And so that's a huge part. And then also, have you actually set it up so that you're only using that test environment when the load test is actually running? And so sometimes people will neglect to do the testing, which is very bad. And then there's a second bad thing, which is you do set up this load environment, but you constantly leave it running, and then you spend too much money doing a load test. So there's a couple different really important things to be aware of when you're thinking about testing your system at production scale. Another one as well is automation. So it's really easy to not automate your system because it requires skill and requires hard work. But with a cloud environment, you should be able to replicate in number of environments. And one way of referring to this that's a bit of a buzzword is something called continuous delivery. So with continuous delivery, what this means is that you can constantly set up and provision new environments and deliver that software to any of those environments in a fully automated way. But if you can't do that, then you're going to have tons of people that are going to be patching together your system to make it run. And people are very expensive. And not only are they expensive, but they make mistakes. So really, automation is one of the most critical components that is not in place architecturally in the cloud. And it's something that can really put a company either in a bad situation or really make them one of the best in class. Another thing to be aware of in terms of architectural principles is this concept of evolutionary architecture. Never is it the case that you start building something and it turns out that it's exactly what you need. Especially in startups, the systems are going to evolve over time, right? And so can you figure out an architecture that allow you to evolve? So one way that you can do this is you can use something called loose coupling. And so if you're building a system and you, let's say, make it a monolithic application, that's not good. What a monolithic application is something where you're essentially putting everything in one system, and it makes it very difficult to pull those components out. But one of the trends here is something called microservices. And with microservices, this allows you to build very small applications that do one thing. It could be as small as, let's say, a function, like a Python function, like this. And that Python function gets deployed to AWS Lambda. And then you don't have this tight coupling of your entire system, and you can evolve over time and change things. And that microservice can either stay the same or it can evolve. So that's a very, very important thing to consider, is that it's a given as well. Not only will things fail, but they'll also change. And what are you going to do to account for that change? Finally, it's easy to have something called hippos. And a hippo stands for the highest paid person's opinion. And a hippo are very dangerous in the real world, and they're very dangerous in the jungle as well. And so what a hippo does is they use their opinion to tell your company what to do. Like, we need to use this type of server, or we need to use this kind of architecture. And what is the antidote to take down the hippos is data, right? And so with data, what you can do is you can make your decisions based on load testing or facts, or make the architectural improvements over time, instead of making someone who has the CEO or the founder or the VP of engineering making the decisions. You can use data to make the decisions and look at actually what the facts are. The hippo can kill many startups, and it can kill actually very large companies as well. And so really the antidote there is to use data. Okay, what about game days? So this is another important principle, is that you actually go through and set up a game day about what would happen in a specific situation, right? So what happens if your company is a startup and you're making $1 million a year in revenue, and you're very excited, you're on your pathway to becoming a unicorn, a great billion-dollar company. And it turns out that, in fact, what's happening is that every once in a while you have this weird problem where customers can't buy products. Well, what you could do is you could simulate a game day, and you could actually go through there and simulate that exact same problem and figure out how you're going to do that. One way that people have accounted for this is something called chaos engineering. And with chaos engineering, you intentionally cause problems in your environment so that you can test out what's going to happen, right? So if you don't plan for the worst case scenario, you're not going to necessarily know what's going to happen. All right, let's talk about some other core principles as well. And one of them is reliability. So what does it even mean to say reliability? So it's the probability that your entire system functions for a specific period of time. This includes things like your hardware, your software, and your firmware, right? And two common ways of measuring reliability would be MTBF, and this stands for mean time between failure, and also failure rate. So the number of failure or total time in service. So it's really helpful to understand a common reliability model when we're actually talking about things. So let's get into the concept of reliability versus availability. So a reliability, again, is how long something is able to function. And then in terms of availability, this is slightly different. It's how often over a percentage of time are the services acting normally, right? And so a lot of times what that's referred to is something like a shorthand. So it could be like 5 nines is something you might hear, or 9 nines. And this stands for the amount of time that this resource is actually up and operating normally. Now, if a really good example of this, in fact, I have a good story about this, is that just because your system is actually up, it doesn't mean it's actually operating normally. And I've seen situations where there's been one machine in 10 that was failing constantly over the case of a year. And so in fact, that system was constantly in a state of failure, right? And so in fact, if you looked at the actual availability, the availability over that year would be, it was available 0% of the time in a reliable fashion. It was constantly failing in a slightly subtle way. So it's a very important thing to think about, that is not only just because it's up, it may be up and performing in a very poor way. Okay, let's get into some of the things about highly available systems here. So, what is highly available? If you look at 1.9, so this would be 90% of the time, that would mean that you're down per year about let's say 2.4 hours a day, right? So that's not good. In fact, I've worked in environments where we had that kind of downtime before. 99%, right? This would be 2 nines. That's something like you're down for 14 minutes a day. And then if you go all the way up to like something like 5 nines, right? So you go 99.999, that would be something like per day, you're down for about 0.86 seconds. And then for the whole year, you would be down something like 5 minutes for the year. And then if you get into like 9 nines, it's like something like for the whole year, you're down, a few seconds. So really important to think about this concept of highly available. All right, let's get into some of these HA components here. So one of the HA components to be aware of is that a highly available system is something that is able to function normally, and downtime is actually minimized, and also that there's minimal human intervention required. So this is really an important thing about HA systems is, are there humans involved here or not? If there's humans involved, then that's not a highly available system. So some of these things that happen with this is in a fault tolerance environment, this means redundancy, right? And then in terms of scalability, this is being able to handle growth. And then in terms of recoverability, this is the ability to restore a service afterwards. So these are core components of highly available systems. So fault tolerance, though, is often confused with highly available, but fault tolerance really refers to the built-in redundancy of a component and the ability to remain operational if some of the components fail. Fault tolerance really relies on specialized hardware to detect some problem, like a load balancer. The fault-tolerant model doesn't address those software failures, and this is a lot of times the most common reason for a downtime. Scalability is something where it's how much your application can respond to the need to increase capacity, but it doesn't guarantee availability as well. And recoverability is also overlooked as well. What happens if you have an outage and you're completely wiped out, but your data is in, let's say, offsite storage? If it takes you 1 month to recover, is it possible that you actually go out of business? So you may actually have, in the case of a disaster recovery service, completely archived all your data. But if it takes too long to get the data back, in fact, you would go bankrupt. So there are lots of really interesting things to think about when you're breaking up architecture, and it's important to fully consider these factors when you're building a system on AWS.